We are live. Go ahead.
So, hello everyone, welcome to yet another episode of IAH and happy Republic Day to all. So, this is a special episode, and I'd like to introduce all the, uh, let's say, panelists here. We all know Saudioja, and this time I'm glad to introduce him as founder and CEO of Deep Purples. And we also have here Dr. Chari. He is also co-founder and chief technological officer of Deep Purples. And of course, Sridham Tyagarajan, he is head of operations, again, Deep Purples. So uh, I'm Aditya Krishna Menon. I hope some of you know me from Twitter. So, well, that's it for the introductions. Let's jump into it right away. I'll hand it over to Saudi.
Okay. Thank you, Aditya, for those kind introductions. So, as Aditya just mentioned, this is a very special episode of Indigenization Appreciation Hour. Sriram and I are panelists in this particular episode, and we are really very happy and honored to introduce Dr. Chari to you because Dr. Chari is at the heart of our new venture. Our new venture is called Deep Propulse, or it's actually called Deep Propulse Aerospace Private Limited, but Deep Propulse for short. Its brand name is Deep Propulse. And as some of you might have already guessed, it works on it at its core is the development of rotating detonation engine technology, which has initially been progressed by none other than Dr. Chari, who is one of India's most eminent scientists. He's a pioneer in pressure gain aeropropulsion technology in India. He served for 35 years in the Defense Research and Development Organization, or DRDO. He was one of the prime designers, if not the prime designer, for the integral rocket ramjet that powers the Akash surface-to-air missile. And he was also the progenitor of Project HSTDV, right? The scramjet project, the scramjet engine project. And it is while he was head of that project that you saw that first 22-second ground test that some of you might remember, in the 2010s. So that is when it happened. Of course, the scramjet program has progressed quite a bit since then, and recently you've even seen 720-second and 1,000-second tests at that new facility that DRDO has on the outskirts of Hyderabad. So it is really, we want to introduce him and his work to you in this world. Deep Propulse is, of course, a company. I am the founder. Dr. Chari is the co-founder. Sriram is with us. Right? There are others too. We have a very strong technical team, and we are dedicated to progressing rotating detonation engine technology for India, especially for strategic applications. So let me just hand this over to Dr. Chari for a bit for him to talk about his journey in the field of pressure gain combustion, and specifically rotating detonation engine technology. Dr. Chari, please.
Yeah. Thank you, Mr. Saurav, for your kind words. In fact, my journey started with the air breathing engine. Okay. So, air breathing engine has become a passion for me because of Dr. Saraswat. Presently, he is the a man in Niti Aayog. Okay. So he has been my mentor, and then, in fact, he was giving me directions at each and every stage of my work, whether it is for the Akash or for the second project, the HSTDV, scramjet propulsion, and this particular RD propulsion also. Okay, so the air breathing engine work started in DRDL for Akash as an integral rocket ramjet propulsion system. Okay, so a new technology which Dr. Kalam wanted to bring in to DRDL. So he has formed a small team of people. I was fortunate to be there in that team from 1982 onwards. So I was there till 1986. 1987, in fact, I went to Institute of Armament Technology to teach missile propulsion to the services. Okay, having finished that tenure, I was asked to come back to DRDL. Then I took over as the head of the scramjet engine division. So after that, I became the project director of the HSTDV, the first hypersonic air breathing technology vehicle of India. Okay, so the air breathing vehicle it has started my career. Almost it is ending my career like that. Now,
Oh, your career has a long way to go yet.
okay, thank you.
You have just begun a new journey.
Yeah. Fortunately, after my retirement, I had an opportunity to continue my work on these rotating detonation wave engines. And then after completion of the work, I could really establish the hydrogen air-based system for about 10 to 15 seconds of duration. Okay, so we didn't have much of facilities to measure thrust and other things. So that I wanted to do it in the present, the D-propulse. So that's why when Dr. Saraswat and Mr. Shaurav called me from Delhi, I readily accepted to, start working on this particular problem of the rotating detonation wave engine. Already, I had an experience of testing this particular engine. Here, we thought that we can put this engine as a prime mover for an air-breathing missile. Okay, again, the air breathing is coming into the air breathing missile, so which requires the nozzle. That's a very important aspect here. So the nozzle, combustor, the intake. So the intake is a very important thing to ingest air to the combustion chamber. So the intake, combustor, and the nozzle combination, which now we are in the process of completing the design, then that hardware will be made and tested so that we'll get an idea about the interactions of the combustor with the air intake. Okay, so we didn't have any problem with the nozzle because nozzle is basically a aerospike nozzle which can produce additional thrust for the forward motion of the vehicle.
Yeah, and is naturally compatible with the annular chamber that a rotating detonation engine has.
True. That is quite naturally, it is very much compatible with our RDE combustor because RDE combustor is annular combustor. So that annulus, straight away, that gases coming in the annulus can be expanded in the aerospike nozzle to give additional thrust to this particular system. Okay, so that is what actually we are planning in this D-propulse, and I must be really thankful to Saurav for giving me this opportunity and getting me money to do this particular job.
We'll come to that later because that's another thing. But yes, we have. There will be an even bigger announcement day after tomorrow. So let us keep it that. But Dr. Chari, it is not. You don't have to thank me. We must thank you for dedicating your life to things for India. Right? And we will move heaven and earth to get you the resources you need. So as Dr. Chari mentioned, the progenitor of all this is none other than Dr. V.K. Saraswat, right? Former chairman DRDO and member Niti Aayog and our chief mentor. He's the chief mentor of D-Propulse. So it was I had gone to meet him in Hyderabad. And as you know, I am sort of obsessed with aeropropulsion, and I mentioned the domain of pressure gain combustion, which is when Dr. Saraswat put me in touch with Dr. Chari, and then we started working on this, and we created this company, which is now already at TRL 4+ with its RD combustors. So to show you what has been done, we have these air breathing combustors from all the way from 2.5 kilonewton to 5 kilonewton. Already working on the bench, of course, for 10-15 seconds, as Dr. Chari said. But we are working assiduously towards increasing the duration. Sriram, would you please play the video of our tests? Yeah, then I'll take people. Then we'll take our audience through the tests on that to show people will get a clearer picture of where D-Propulse is at the moment in terms of technology development. I have also shared the link to our website. Please check that out. Right. And okay, some people asking D. It's not DE. It's D dash Propulse. Right. That is the brand name of the company. So let us just play the video. I think Shriyam is transitioning to the video. Yeah. Okay. What you can see now is you can see the first 5 kilonewton combustor created by Dr. Chari in operation over here. This is an air breathing system, which is why you don't see and this is actually a test at DRDL. There are a couple of test videos which have been put together, but this was a 15-second test. And the flame that you saw is the kind of flame you will sort of expect with an air breathing system, not some typical bluish flame where hydrogen and oxygen are being mixed at a perfect stoichiometric ratio or something. This is the kind of flame you'll expect when an actual air breathing RD is in operation, which will not give you that standard kind of frame. Okay, so can we switch back to? We'll play that again for viewers who join us later. Can we switch back to the discussion, please? Right. Okay. So Aditya, why don't you? I'm sure you have a few questions to ask as somebody who's been looking at this arena for a while. Why don't you go ahead?
Okay, so firstly, bench test at DRDL, I believe this was done. And
yes, it was the second where you see the clear annular flame that was tested at DRDL. Yes.
Right. I mean, first of all, what is the let's say current facilities that you have that are outside of, let's say, DRDO support
So we are the Deep Propulse has been incubated at IIT, is now incubated at IIT Madras. Right, it didn't start off that way, but it has now incubation status at IIT Madras, and we have access to facilities at the National Combustion Center for Research and Development, which was incidentally set up at the prodding of Dr. Saraswat. But beyond that, we are creating our own bespoke test facilities that you will see in the months ahead. Right, we are also increasing our compute hardware, our own compute hardware and stuff. But this is a very pertinent point, right? You need your own test facilities if you want to cycle through quickly.
As answered that point, is that the pressure gain combustion. See, in almost all the engines today, they use deflagration wave. Okay, that is, they propagate at subsonic speeds. That's number one. Whereas here we can have the detonation wave, which is actually moving at supersonic speed, and then we'll have a pressure gain combustion. Pressure gain meaning it's not static pressure. It is total pressure gain combustion which is happening there. Okay. Of course, that has been a challenge, whether how much gain we'll have. In fact, these challenges we also faced when we were developing the scramjet-based system, wherein whether we'll have a T minus D, thrust minus drag, positive or negative. So in a similar way, here also we are addressing the point that whether this pressure increase, total pressure increase, is going to be positive, or the difference between the total pressure at the exit minus inlet. Okay, so whether that is going to be negative. So that's a figure of merit for the propulsion system. And the another aspect is that it is efficiently burning in the detonation wave, this particular fuel and oxidizer. So you don't have the pollution problem. That's number one. Then number two is your thermal efficiency increases by 25% compared to gas turbine engine or normal ramjet engine, turbojet engine, all those kind of things. Okay, so we are scoring over in almost all the fronts. Of course, Saura used to ask me what will happen to the heat transfer aspects. That is a real aspect which we'll have to address, because at a particular axial distance, this rotating wave, detonation wave is anchored there and it rotates. And the rotational frequencies are of the order of 5 to 10 kilohertz. So something like you have every second, this reaction is rotating 5,000 times or 10,000 times or in between of that order. So that is actually a real challenge, and keeping that stable for a longer duration is another challenge which we'll have to overcome. I have absolutely no doubt that if we work very hard, we can overcome this. Okay.
Right. Sriram, you're muted. So just, going further with what Dr. Chari is saying, this is a ramjet is ultimately a pressure loss system, right? And a rotating detonation engine is a pressure gain system. You must note that while a rotating detonation engine will also need a certain amount of compression, a certain amount of ram compression, air breathing. I'm talking about an air breathing rotating detonation engine, because if you don't have enough air molecules in there, then you will not be able to sustain the rotating detonation wave either. It will not have enough to play with, basically. I mean, you also need enough oxidizer in there, right, in the form of the air. So the thing is that, but in the case of a rotating detonation engine, most of the compression is done by a supersonic rotating detonation wave that
Excellent.
moves along. Yeah, which is what compresses the fuel mix and raises it to its auto ignition temperature, right? Instead of you don't need a flame holder, obviously, but what you do need is a pre-detonator. A pre-detonator is like this tube which sticks outside, or it could be even engineered to be inside and not visible. But that is the one which sets up the DDT, or the deflagration to detonation transition, and sets up the rotating detonation wave inside the annular chamber. As Dr. Chari was mentioning, the heat flux is an issue here, because unlike a ramjet where it is distributed all along the combustion chamber, all across, this sort of has foci, right? The heat flux has foci. You have to be able to predict where the rotating detonation wave or the detonation strike will happen on the annular chamber. That is where the heat flux will be focused. So that is another thing, but that is exactly where we step in, right? Where DPropulse steps in, where Dr. Chari's team steps in, where those are exactly the problems we are looking to solve. And once we know all that, why does that matter? That matters because if you know exactly where the heat flux will be concentrated, you can choose materials that are relevant to that kind of heat flux distribution, and you can have gross savings in terms of the weight of the engine. In any case, the engine will be smaller and more compact than a ramjet of equivalent max thrust levels, right? Because of the pressure gain, because this is going to be in any case up to 25% more thermally efficient.
Yeah.
And so that the confluence of those two factors, greater thermal efficiency and lower material inventory cost, is what gives you a much better thrust to weight ratio and leads to savings. If you have a 5 kilonewton engine, remember something, the Manik turbofan that powers the Nirbhay family, now called long range land attack cruise missile, that's 4.41 kilonewton, right? So the engines we already have on the stand are 5 kilonewton engines, 5,000 newton. So if you have something as compact as the kind of engine we showed you, you can obviously build a much smaller vector around it also, subject to certain caveats, right? There is the detonation hammer that you have to take into account, vibration levels, acoustic levels, all that you have to manage. But all that is a matter of development. If it was all already done, then these are the only things you would see flying around. So that is the real joy of rotating detonation engine technology, and why it is an absolutely critical technology for India, which is why we are here really, which is why we have staked everything to make this happen. And that is how we are going to go forward. And of course, we need everybody's support, because as you know, we are inclusive and we know that we can't do things by ourselves only. Others need to come forward. In general, people who are interested in combustion dynamics, in aerodynamics and all, will be able to apply to us also. We have a place in our site. I guess we can even. I shared our this with you. I shared our website address with you in the chat box. Yeah, Aditya, can you pull up our website, please? Would it be possible?
Yeah, sure. Give me.
If you are interested in CFD related to detonation logic, stuff like that, please do write to us. We are looking to recruit talent, as it were. Fluid system specialists are also welcome. People with interest or expertise in aerothermostructures, they are welcome as well. And generally others who might have studied some other discipline but are interested in these things. So this is our website really. Our website has that video probably on a loop right now. So just scroll through a little bit. So see, this is the solution. This is a cross section of one of Dr. Chari's initial RDE designs, right? This is a cross section of that. You can see there's a from pre-detonator and stuff like that. There's much more on our website. You can go to our website, and we will also be releasing, sort of explainer videos in the months ahead. So you should go to our YouTube channel as well, where we'll be putting up videos and documenting our entire journey as we progress this technology for India. So we have so we just wanted to use this this holy occasion, I mean Republic Day, to unveil this thing. I didn't unveil it months ago, but you'll understand why soon enough. But a lot of work has been going on, and as you can see, we already have working 5 kilonewton combustors, and Dr. Chari is working on flight rated iterations of that. Flight rated iterations are currently being designed with new materials, much lighter materials. Also, what we are doing is we are moving we are going to be experimenting on a range of fuels, hydrocarbon fuels already. Obviously, from everything from Jet A1 to JP10 will be on the menu to see what really works best with this, keeping in mind the techno-economics. Because the idea is to provide our warfighters with mass in precision. The high supersonic and the hypersonic age, as you know, is quite expensive. I mean, you have to make it affordable. And this, in our view, is the answer. So in some sense, RDE will be to the to the 2030s what the gas turbine was to the 1950s. And as you know, we are not the only ones working on this. The Americans are working on this, the Chinese are working on this, the Russians are working on this, and the Japanese are working on this, and the French are also working on it. And even the Poles have worked on it, of course, in association with Boeing. So, and you must have seen releases in recent times, from GE and Lockheed Martin, also from RTX, which is working on a DARPA program. There are some 9 different Chinese institutes who have a hand in RDE technology. Some of them also work on oblique detonation wave technology, another form of pressure gain combustion. We will probably also work on that at some point for even faster vectors. But right now, our agenda is to have a strong technical team progress our proprietary technology rapidly towards TRL9 and into production. Right? That is our agenda. So that is what we are working on, and that is what Dr. Chari has dedicated day and night to at the moment. Right? And we are supporting him as the best as we can. So Dr. Chari, why don't you again speak about the prospects of this technology, in the sense that what else can, once we crack the first air breathing systems and build effectors around it, what else can we do with all of this?
Actually, apart from munitions, you can think of even the power generation using this particular technology. That is what we also had a discussion some time back. So that will also come based on the hydrogen setup, where that is now everybody is talking about green gas and things like that. So we'll be having hydrogen, and then which has got only a water vapor as the the exhaust. So it doesn't have pollutants and things like that. So we can comfortably use that for our power generation. And then the other aspect what we have been discussing is about the combined cycle engine. Okay. What GE is also trying to develop that is, so we'll replace the low pressure, high pressure compressor and high pressure turbine using and the combustion chamber using our RDE. So RDE doesn't need much of a increase in pressure, because RDE is going to increase its pressure 15 to 20 times in case after establishing the rotating detonation wave. Okay, so let us say if your entry pressure is about 2 to 4 bars, so it will be about 15 times more in case if you use hydrogen as a burning material. That so these kind of a compression we are going to definitely generate, but in order to have an initial compression of this, we can have a low pressure compressor, and then in order to rotate the low pressure compressor, it is as well sufficient to have a low pressure turbine. Okay, so with this we can think of a combined cycle engine. In fact, in our country we have not really started working on that. No institution, no laboratory is looking at that. Hopefully, once we start, probably somebody may be motivated to help us, or somebody may be motivated to parallelly work on that particular aspect. So that is another big area in which we can think of. So the power generation, and then the combined cycle engines or propulsion. We can use it for propulsion. That is the single stage to orbit, those kind of things are possible. Okay, by this. In fact, we have not touched upon the satellite area yet. Okay, so that is another big business. Potential. So for that also we should be in a position to offer our solution. We'll mature it and then we'll do it definitely.
So, as Dr. Chari outlined, rotating detonation engine technology is a GPT, a general purpose technology. It is actually no less important for transportation than, say, electricity is in some ways, or electricity is for the industrial applications as well. He did talk about satellite launch vehicles at the end. So just like you have an air-breathing rotating detonation engine, you can have what is called a RDRE also, a rotating detonation rocket engine. You can you can have an RD combustion chamber in a Methalox kind of setup or a Kerolox kind of setup. That is what NASA and JAXA and all have focused on actually. And even in the Methalox kind of setup and with the use of GR-COP 42 as the material, NASA has managed to reduce the length of a typical Methalox engine by 60%, right? Or 40 to 60% in that range, with the concomitant savings in weight. So, if you want to really take on, one of the ways in which you brought down the cost per kg for orbital launch, for LEO and general orbital launch, is reusability. But this is actually what will really bring down the cost per kg for orbital launch as this technology matures, because it will bring down the weight of the vehicle itself by a huge fraction. And you'll also be able to address different kinds of orbits. It will increase versatility of a single satellite launch vehicle also. And of course, when you couple it with, and if you can couple it with reusability, then nothing like it. Then you have a kind of a sort of a golden new kind of setup altogether. But these are things in the future. At the moment, we are working on air-breathing rotating detonation engines with different types of fuels being considered and experimented upon also. And the idea is to give the warfighter, the Indian military, mass in precision. That is the real idea. So we are assiduously focused. We are laser focused on that goal right now, and that is what DPropulse is doing. Shyam, you wanted to say something?
You were talking.
Yeah, so 3D printing, of course, is something we are looking at closely, because anything which requires active cooling, you typically think about 3D printing also nowadays. It sort of rings in your head. What will be used, what will not be used will, of course, these are all choices that Dr. Chari's team will make over time, is already making. And but Dr. Chari, what do you think is the ultimately, when you look at this, what is the kind of time frame in which we will see all this become ubiquitous? This particular RTEs become ubiquitous. I said the 2030s. When do you think in the 2030s will we see this sort of start replacing the gas turbine in general, and not just ramjets and scramjets for high-speed applications?
See, the what we have to really establish here is about the liquid fuels being used in RDE. Okay. See, gaseous fuels, there will not be any problem of getting the detonation. But liquid fuels, people face problems in abroad for a simple reason that it is very difficult to ignite, even by using a let us say a pre-detonator, like whatever you have mentioned about the pre-detonator. A real bang which happens inside the pre-detonator, and then the detonation wave is entering, it ruptures the diaphragm, enters the main combustion chamber, which just suddenly ignites, and then your detonation wave is formed. So there are certain prescriptions for the liquid fuels. One is you can have a finely atomized liquid fuel. That's number one. Number two, in case if that is not adequate, then we can add either hydrogen in small quantities, or we can have enriched air, that is, enrich the air with oxygen. Little bit of oxygen you add to that. See, the present one air contains 23% oxygen, whatever we breathe here. Okay, but you make that about 32%, that oxygen, by externally adding extra oxygen. So that can easily ignite the situation. The another one is heating up the fuel itself and making it to the vapor. Okay, by some means onboard heating of the fuel itself to make it as a vapor. And vapor can easily, it is almost a gaseous state, it can easily produce that's what people written, it can easily produce a detonation wave. Yet another one is you try to heat up the chamber, the cold chamber walls, you just heat up to about 100 degrees centigrade or 100 plus degrees centigrade, so that your the chamber is not cool, chamber is hot. See, what really happens is that this free radicals which are getting generated, they actually die on the walls of the combustion chamber, because walls are cooler. Now you don't allow the walls to be cool. You keep the wall always hot. Then that possibility you can avoid, and then you can establish the detonation wave. So like this, there are various things which people have been they have prescribed, and they have been working on that. Over that, what I would like to say is that the correct way of atomizing or injecting the fuel and oxidizer inside the combustion chamber. So that area will have to really work hard, because there are basically two things in this. One is the isolated RD.
Yes.
That is, separately you look at RD as a combustion chamber, you want to prove the combustor only, or combustor plus aerospike nozzle, that combination only, without introducing the air breathing aspects of that. That is, you supply air from the tanks and then do the test.
And then connect
Probably
pipes.
that may be useful to the extent of probably getting an academic degree or something like that.
Yeah.
Whereas if you want to really make a system which is going to work, particularly in the case of munition or such kind of things, we need to have an air breathing RD. In that, air intake becomes an important aspect. Now, the moment you have an air intake, the air intake performance also you should look at it carefully. And you have the combustion chamber entering entry, you have the air intake, air entering inside. So if that is providing some resistance in terms of some fine holes and other things through which you are making that air to pass through that, it doesn't really happen. Okay, so immediately it transmits the a shock from the downward to upstream. So your air intake shock is getting thrown out. That kind of operation, what we call it as subcritical operation of the air intake. So these are all the things we have come to know based on the CFD studies, whatever we have been doing now, right now. Okay. So in tandem with our combustion chamber, this how this air intake works, that we have to really sort it out. So that is why we are now planning for a kind of a semi-free jet testing, wherein air intake combustor and nozzle total this thing integrated vehicle will be tested. There we'll get a lot of ideas. The moment we win this problem, I think we can go to any reach, any application, whatever we are thinking of, we'll be in a position to solve it. I'm just confident about that.
Right.
So I'm unable to give you dates like 2030 what will happen and 2035 what will happen. I am just going ahead with the one event, a successful event. We'll know that time is not a big issue at all.
Yeah, but it's a threshold crossing event. And if it is crossed, whether I think it will be crossed, then all those 2030 projections will definitely come to pass.
Definitely. Yeah.
So,
So
Aditya,
we know the. There are many things, known unknowns are known.
yeah.
Okay.
There are known unknowns and there are unknown unknowns.
Okay.
Obviously.
So unknown unknowns, we will have no problem. We do not know how it is working. But that will come. We will come to know once we have a flight.
What
Yeah,
if
there are-
something is if something is destined, then you get to know the unknown sooner than later. Okay, Aditya, you were going to say something, I think. So
Yeah, I think most of the questions I had were covered, but just one thing. Currently, we are using a hydrogen oxygen system, I believe.
no, a hydrogen air system.
Air system. Okay.
Yeah, not a
Eventually,
hydrogen.
eventually you'll have to transition to a liquid fuel, right?
Yeah, we are going to
For most
transition
applications.
entirely to liquid fuels.
Right. So when do you see that happening? And when will you begin testing with those sort of fuels? And secondly, you mentioned the applications. What exactly can be made from this? Because if it's more compact than a ramjet, then there are many additional opportunities, right?
So we are going to transition to. We have already transitioned to liquid fuels. We are going to test liquid fuel combustors in the very near future. Okay, very near is what I would say. And we would test scaled up ones even in about 6 months' time. Large liquid fuel combustors will start working. We'll start seeing them working and everything. And you will start seeing if all goes according to plan as we were just discussing, you will start seeing large liquid fuel combustors in another 14 to 15 months' time. Large ones, right? 10 kilonewton plus. Now, as far as the applications, the main, like I said, the confluence of those two factors, where it's more compact, material inventory is lower, and yet, you reach the same amount of thrust as a ramjet with a smaller engine, that opens up a whole arena of possibilities for you. You can now have a smaller airframe built around this engine, which will be compatible with many more. Say you have the BrahMos on the Su-30 MKI, and because you want to have the BrahMos on many more systems, you're coming up with the BrahMos NG. Similarly, you can have a 5 kilonewton powered system that is compatible with the whole range of aircraft. A 5 kilonewton RD powered system because of its compactness. You can have the same warhead weight, yet the all-up weight will be lower because the engine weight will be lower, the warhead weight will be the same, and the overall airframe will be smaller. And yet you will manage the same kind of distance, maybe at slightly higher speed. Right? So that is the kind of gain you can get out of this. And you can reuse all kinds of other things. The guidance and navigation control package you can reuse from a legacy system. The Seeker also you can reuse from a legacy system as long as you are below Mark 4 in terms of your terminal, in terms of your end game. You can use something which is any. And see, again, we are building on the shoulders of the work that Dr. Chari and his colleagues did at DRDO in terms of creating an industrial ecosystem for India in the space of missiles, right? Today, when I have to procure a Seeker, I can think of 3 or 4 companies that I can go to in India itself. Same for the GNC package. Same for most of the aerostructures as well. This is the kind of luxury that, say, Dr. Saraswat definitely did not have when he was progressing the Prithvi project in the 80s and the 90s. Right? There are hundreds of stories of how what kind of problems they had to solve to make that system happen. I think you can hear me, right? So
Yes.
coming to, I think we need to talk about Dr. Saraswat a bit over here, because know one thing, Dr. Saraswat, after all, delivered a missile, a short-range ballistic missile, liquid fuel, by the way, okay, which has been produced in India in some numbers. It was actually produced in reasonable numbers. So that sort of set the tone in many ways. A lot of people think, what was the utility of the Prithvi SRBM? The utility was immense. It created an industrial ecosystem in India. At that time, you did not even have what is called the MSQA, right? Which is the sort of the DGAQA for the missile sector. So we are building on a whole journey, and the whole point is we need to crack the propulsive side of things, which Dr. Chari has already progressed quite a bit beyond TRL-4. So while we need to master fine spray atomization techniques for liquid fuels, as Dr. Chari was delineating, and we need to also, have the right, absolutely panned down models for heat flux distribution. But those are things that you will be able to crack provided you stay at it. And that is why DPropulse has been made. DPropulse will use the kind of discipline that a private company brings to the table while working assiduously in the deep tech arena, while creating intellectual property for India. That is the idea. Because we are looking to address India's key Achilles heel, right? Which is aeropropulsion and the lack of intellectual property in that domain. That is what we are looking to sort of address. So we are at it, and we, as Dr. Chari has outlined, we are also, we welcome talent within India who want to work on this key area, because this is going to be to the 2030s what the gas turbine was to the 1950s. All the major power centers of the world are progressing it, right?
Right. So since you mentioned the ecosystem, evidently you will need a lot of expertise, talent in various fields, and plus you need suppliers and other firms to supply certain materials, say injectors and all that. So what is the level of partnership, any interaction that you have right now with others, including DRDO and private sector, and what can it look like in the future?
Yeah. So we have had initial talks with government stakeholders, and as far as the supply chain is concerned, we actually have vendors already on the fabrication side. We have vendors on the test rig side as well to help us set up test rigs. Those who worked on programs before, similar programs that Dr. Chari himself had sort of originated at one time. So we have, we are clued in with the ecosystem, but of course we are always looking to onboard new vendors, new players, build relationships. Because as I keep saying, this effort is not happening in a vacuum, right? It is an effort that will require many stakeholders to sort of chip in and chime in. Already we have seen movement in that arena, and as I said, we'll see more movement. In a couple of days, you will see something. You'll see another big announcement, a bigger announcement maybe than this one was. So we are there. We have the initial resources required to progress this beyond TRL 7 or 8. So, and of course, we'll have to gather more speed and gather more sustenance, if you like. But that is, in any case, what this whole deep tech arena is about anyway, right? Yeah, go ahead.
Yeah. So and evidently, I mean, I don't think we have a national, let's say, aero propulsion mission to speak of. So, but we are taking some steps towards that, say with the Safran engine and all that, right? So, what sort of government, let's say, involvement, MOD government, what sort of backing do you think will be required?
for this. So there are these well-known programs, and we will be looking at each of those. I guess it is not the right time for us to discuss precisely what those are, but we expect support at the moment. We do expect support for this because I think some people have realized how critical this can be and why we need to not fall behind the way we did in the arena of gas turbines. Right now, in gas turbines, we are in catch up mode. We are having to invest sink a lot of capital to catch up, basically. And we will catch up with the grace of God, it maybe by 2034 or 2035 with the program that you mentioned, right? The partnership with Safra. But in the meantime, we cannot afford to fall behind in the emerging areas of aero propulsion. And rotating detonation engine is definitely the front runner as far as the emerging areas of aero propulsion is concerned. And that is what DPropulse is looking to address and will address. Will address that specifically. Shriram, you wanted to add something to that?
Not yet. See, okay, let's hope I'm audible now. Third time
Yeah.
is down.
It's audible here.
The thing about propulsion systems is that we've always been behind, right? So, in terms of any kind of propulsion technology, we've always had license building engines or fully built out systems. So now, hopefully, our efforts should give us technology that can put us on the same keel as the rest of the world. So that's the aim, right? So if you have experience, or if you're in the field of the kind of technologies that Saurav and Dr. Sari were talking about, right? So any shade of mechanical engineering, or even electrical engineering in embedded systems, sensors, and all of that. If you're truly interested in serving the country and want to take a crack at the next generation technology, do write to us. We are very, very interested in taking top-notch talent and taking the country forward. So that's my earnest appeal to youngsters who want to serve the country and in your own fields, right? So especially pressure gradient combustion, aerostructures, aerothermal, studies. We are looking for people like that. So if you're a young guy or a girl, right, who's doing BTech, MTech, PhD, or if you finished any of these degrees and you're working somewhere and you want a real challenge to prove your mettle, write to us. Yeah. That's it.
Sure, I think we can take a few questions as well.
Yeah, one question was, can you put this on a UCAV, on a hypersonic UCAV?
Yeah, you can, but you need a combined cycle plant for that, right? You need a gas turbine in front and you need the RDE at the back, and then you need to shut off all the air to the gas turbine at some point and direct it entirely to the RDE at the back. That's at a velocity in which the RDE will ignite. You need some ram compression for the RDE. So that is the kind of, basically you need what is a TBCC kind of thing, right? You need a TBCC kind of conception, but with an RD instead of a ramjet or something, a turbine-based combined cycle. And then in the very far future, not very far, maybe in the 20 years' time, you can have a conception where the the core of the gas turbine has also been replaced by an RD combustion chamber, as Dr. Chari was saying. There is just a low-pressure compressor and a low-pressure turbine, and behind that is an air-breathing RDE engine using maybe cryogenic liquid hydrogen, cryogenic hydrogen and cryogenic oxygen, right? And that is the kind of thing that may actually give you the kind of TWRs and all you need for single stage to orbit trans-atmospheric vehicle, TAV. That is the holy grail. I mean, this is one of the ways to get there ultimately. Yeah.
There I see the problem is about the blade cooling.
Yeah.
Turbine blade cooling, because the exhaust getting expanded in the RD, they have temperature of the order of about 2800 Kelvin or so, which we have to see that the this turbine blades they withstand. So there may be a kind of diluting the flow and things like that. We have to do it. And there are issues, of course. I mean, unless you touch that area, you will
Yeah.
not know what are all the problems you are going to face.
Yeah, the same thing about known knowns and known unknowns and unknown unknowns. And I saw a question on pre-cooling. What is your view on that, Dr. Chari? Pre-cooling?
Pre-cooling of what? Actually,
It's not really
incoming air.
refrigeration of incoming air. That is not the point. Because somebody, I think, was thinking about the Sabre engine. They're talking about pre-cooling the air itself that comes in.
not necessary, no.
Not necessary.
But we want to have that in slightly higher temperature condition.
Exactly.
So heating, I'll be very happy.
Yeah.
Rather than cooling.
Yeah, we need the preheating of the air rather than
Actually,
the
what we
pre-cooling of the
can
air.
think of is that this is regenerative cooling of the combustion chamber.
Yeah.
Okay.
So, cooling of the combustion chamber, that active cooling, that is understood. Somebody, I
Yeah,
think, mentioned pre-cooling. But the
That is
point
not
is, we
the-
need actually preheating of the air in our case, right? We'll
Yeah,
be
yeah.
happier with that. Ah,
No, once we have a low pressure compressor,
ah,
as it compresses, it heats up the flow also.
yes.
A moderate heating is possible using that. Okay. It will not be at room temperature, it will be at a higher temperature only. But what I would like to think of is the regenerative cooling of the combustion chamber, so that this high heat flux values, the high heat flux thing coming onto the metallic combustion chamber, that we have to protect. Of course, there are certain ways in which you can avoid that. May not be possible for a very longer duration, like antioxidation coating, thermal barrier coatings, zirconia and YSZ and those kind of things. Okay. And then this regenerative cooling.
So,
But cooling by the same
fuel.
fuel.
Yeah.
That will be advantageous because fuel is already heated up. Okay. It may not go to vaporization temperatures, but still it is fairly heated up.
And what about the issue of, when we have a low pressure turbine also, say that scheme, where you have a low pressure compressor, RD combustor, low pressure turbine. But the RD's exhaust will be somewhat intermittent. I mean, not intermittent like a pulse detonation engine, but somewhat intermittent. How do you synchronize, or synergize that low pressure turbine with that kind of an exhaust?
No. See, that is why, though when process-wise intermittent, if you really look at it, the RDE operation, it is something of the order of 5 to 10 kilohertz. So 5 to 10 kilohertz is a fairly, very good speed. So that we can as well assume this to be a continuous process.
And especially if we could, put an aerospike nozzle, although that I don't know how that works in the case of a low pressure compressor also being there at the low pressure turbine. But the aerospike nozzle also.
No. The moment you put your this thing turbine there, you can as well dispense with the nozzle.
Nozzle, yeah.
We will not be in a position to use that nozzle.
Yeah.
Actually, we are going to connect this to a alternator only for power generation.
Yeah.
We are not going to do actually the propulsion.
So aerospike, does the aerospike nozzle reduce intermittency of the exhaust? Whatever little intermittency is there?
No. It is just only expanding the flow. That is, it is increasing the velocity when it goes through when it expands through the nozzle and brings down the temperature and pressure. That's the only thing it is doing. And pressure goes to the level of the atmospheric pressure.
We are going to soon put out test videos of our new iterations where you will see the RD combustor and the aerospike nozzle in action.
Yeah,
which
yeah.
is one of the
That
reasons
will
why
do
I
it.
brought this up, right?
That will do it.
That we'll do very soon. And like I said, please follow DPropulse's channel as well for updates.
So that Mr. Saura has given me time about 12 months.
No, not 12 months. For the first test will happen just in a few weeks, actually. The initial test.
Yeah,
Right.
yeah. No, that is okay. That is okay.
Yeah.
That is possible.
Yeah,
I mean, there are two things which are there. One is it is under fabrication. The moment it is fabricated, it has to be taken to DRDL for testing. We spoke to them about testing our thing. They agreed, but only time slot we'll have to get.
So anyway, this program will now have to draw to a close. We will have more explainer videos and all on Delhi, on DPropulse's channel about RDs to get more of you interested and invested in this technology, which is a critical technology really. And we will also put up videos of our various tests over time. Routine tests. Test videos will become pretty routine on our channel as the days go by. And we have begun this journey. We have staked. We will give it our all. As you know, I don't do things by half measures anyway. And I don't think Dr. Chari has ever done things by half measures in his life. Sriram is, of course, there to manage a whole bunch of other things. And Aditya is, of course, here because he will now be the host of Indigenization Appreciation Hour here on it. Right? He's very modest, but I can tell you he's one of the most knowledgeable people you will find on defense issues in India, especially defense technology, especially the military industry, our emerging military industrial complex. Given my new role and Shriram's new role, and of course Dr. Chari is here, we are not going to be able to comment on everything the way we used to earlier. We will be on this show, right? But it'll be now Aditya's show essentially. And although he did speak much today, but I'm sure he's going to sort of make up for it in in coming episodes. And he's also working on very interesting things in the materials arena. I won't go into details of that. I'll leave it up to him to speak about it if he wants to. With that, we'll have to bring this particular episode to a close, right? And as I mentioned earlier, today's was an announcement. We unveiled something. Day after tomorrow, there will be an even bigger announcement, right? Please keep your eyes out for that. And as always, taking your leave, Jai Hind.
Jai Hind.